wants us to find the force of interaction between object 1 and object 2, or box 1 and box 2. So let's just go ahead and call these box 1, box 2, box 3, so that there's not too much confusion. And if I can see in my head, it wants me to know what is this interaction going on between these two. Now, this is the same force experienced by both objects, and it's just in different directions. And I probably am going to want to approach this by thinking of each box as its own system, since I see things like friction in box 2, friction in box 3, friction in box 1, all along. So let's just go ahead and do that. Let's say system 1, system 2, system 3, and let's try to identify our forces. First of all, each block is interacting with the mass of the Earth in its own way. So system 1 is going to have a weight force that is M1G. System 2 will have a weight force that is M2G, and judging by the size of the block, I would assume it's maybe a little bit less. And then system 3 and 3G. Now, each of these boxes is also going to interact with the surface. Now, we haven't talked too much about this yet, but we know that there is going to be some friction. And they all have this same little thing mu called the coefficient of friction. That basically for now just means that they all have the same type of surface, and it's fair for us to just think of them as having their own individual frictional forces. So they're each going to interact with the surface similarly, having a frictional force, a parallel resisting force, and then also some force of support from the surface, which would be normal to it or at a right angle, and that would be a normal force for each one. So let's start with system 3. The normal force of system 3 is going to be just big enough to balance the weight force since it's not accelerating up and down. Same thing with system 2, probably a little bit more normal force since it seems to be a bigger box. And then system 3 is going to have a normal force. Sorry, system 1 is going to have a normal force that is also equal to its weight. Now let's add in the friction. System 1 is going to have some force of friction from the interaction of its surface with the surface of the table. And block 2 is going to have some friction from its interaction. Block 3 is going to have some friction from its interaction. So I call those frictions of 1, friction 2, friction 3, and so forth. Okay, now I think about where does this external force go. The external force is only directly applied to object 1, so I can only apply it to object 1. I'm actually going to make it a little longer because it needs to be bigger than this frictional force. So I call that capital F and I put that there. So where are the other forces? The other forces come from these interactions. Object 1 interacts with object 2 interacts with object 3, and each of these shares some force of interaction between them. So let's first talk about the interaction between block 2 and block 3. Block 3 is going to experience the interaction to the right because it'll feel like block 2 is pushing block 3. And block 2 is going to experience the interaction to the left because it'll feel like block 3 is sort of resisting block 2. So how do I show that? Well, the force of interaction between 2 and 3 is felt by object 3, right, as its own system to the right. And the force between object 2 and 3 for just system 2 is to the left. So that is the same force, it's just that it's experienced to the left. Now we think about object 1 and object 2. Object 2 is going to experience the force of interaction to the right, so I feel like 2 is being pushed by 1. So I would say force of interaction 1, 2. And object 1 is going to feel that force to the left because it'll feel like it's being resisted by block 2. And 1, 2. Now, what I use is to create equations for each situation. It's pretty simple. Now, I see that the y forces are all balanced out. And for right now, I actually don't need to think about too much vertical stuff. So I'm just going to write only the horizontal forces for each system. The horizontal forces for system 3 are going to be that force of interaction between 2 and 3 minus the friction of object 3, and for this problem, constant velocity, the acceleration is 0, and let's assume that this velocity is to the right, and that means that I can say that these horizontal forces all add up to 0. Now, this means that the force of interaction between object 2 and object 3 is just equal to the friction of object 3. Now, if I add up all the x forces for system 2, I have force of interaction 1, 2 as a as a positive force, and then the force of interaction between 2 and 3 as a negative force. force, which in reference to system 3 is actually a positive force. So this is that equal and opposite action-reaction pair that you get from Isaac Newton's idea of the third law. There's also going to be some force of friction between the surface of block 2 and the surface it's on, and as long as there is constant velocity, these will all add up to 0. Great. Now, I can think of system 1 while I'm at it. It's not that big of a deal. I'm going to have that external force. I'm going to have friction, and then that force of interaction 1, 2, and all those are going to add up to 0. So what do I actually need to solve this problem? Well, if I know that the force of interaction between block 2 and 3 is equal to the friction felt by 3, and I put that here. So that means F2, 3, we're going to take magnitude and we're going to put it there. Then what I get is the force of interaction between block 1 and 2 minus the force of friction experienced by object 3 minus the force of friction experienced by object 2. If all this adds up to 0, then I actually get a pretty simple equation for the force of interaction between object 1 and 2. And that would be F12 is going to equal the friction of object 3 plus the friction experienced by object 2. And again, I can switch those around, and that's answer C.